In this video, we'll be looking at doing and predicting what will happen for organic reactions. So the first thing we want to think about when we're dealing with organic reactions is almost every organic reaction that we're going to talk about involves functional group changes. So right away, what I want you to do right now is pause and kind of do a little assessment on where you stand on functional groups. So if you're still kind of struggling a little bit with writing names and structures for functional groups, what you should do is you should not continue this video, stop it, and then spend some time working through functional groups, both in terms of writing organic molecules and naming them. Organic reactions are best done when you are very, very confident already with what's happening with functional groups and recognizing functional groups. I can't stress this enough, is if you're not comfortable with functional groups, you're not going to be able to really handle dealing with the reaction. So take a moment, do a real honest assessment with yourself where you stand on functional groups and recognizing functional groups and naming functional groups and writing structures for functional groups. If you're okay with that material, then it's okay to kind of continue on dealing with reactions. If you feel you need more work with some basic functional group work, then you should not continue this reaction video. Spend that time getting as good as you can get with functional groups before dealing with the reactions. This is why we waited for the reactions till all the way at the end, because reactions are best done when you are comfortable with everything else involving functional groups. So in these organic reactions, one functional group is going to be transformed into another functional group. And what we're going to see in a lot of these organic reactions is if a new bond is made, then an old bond must be broken. And that kind of makes sense because we know that carbon can only have 4 bonds. If we're trying to make a new bond with a carbon, we would have to get rid of an existing bond. So that's what we want to think about. If we're bringing in something new, something old has to be gotten rid of in order to make room for that new thing. Another thing we're going to see with a lot of these organic reactions is that every part of the molecule that's not part of the functional group remains unchanged. The only manipulations really happen, the only change parts happen with the functional groups. The rest of the molecule stays exactly the same. We're to kind of put this in a non-chemistry analogy. Kind of the one I would use is the imagery of a train. If you can think about a train, it's the engine of the train that does all of the work. That's the thing that's really moving and driving the train. Even if you had 100 boxcars hooked up to that engine of the train, it's really only the engine. All those cars are just going to follow along wherever that engine pulls or pushes those cars. Same thing with the functional group. The rest of the molecule is just going to go along for the ride with whatever's happening for the functional group and remain unchanged. So that's going to be a key part for a lot of these organic reactions that we're going to talk about. Our very first organic reaction isn't functional group dependent. Here we don't even care about the functional groups. We're going to knock this one out right away before we get into the real organic transformations. And this is a combustion. This is probably the least interesting organic reaction. We know that all organic compounds are flammable. Does that mean? That means they burn. It's just that when we actually combust an organic molecule, we don't change it into another organic molecule. Instead, when we burn an organic molecule, when we burn those, we break those down into inorganic compounds. So what happens when we burn something? Well, when we burn something, we're taking an organic molecule, we're exposing it to oxygen gas and sometimes a little spark or a little heat. But what are the products that come out of it? Anytime you burn something, when you burn an organic molecule, you're always going to make carbon dioxide and water. Well, carbon dioxide and water, those end products, those are not organic compounds. Those are inorganic compounds. So the act of combustion, what really happens is you're destroying organic compounds. You're changing that organic compound into an inorganic compound. And we can see this here. This is the one reaction where we don't really care about the functional groups. We don't even need structures. See, we can generalize this, highlighted in yellow. Any sort of organic compound. I didn't draw a structure. I didn't even give you a full formula. Any organic compound that contains carbon and hydrogen is potentially flammable. It'll burn with oxygen gas. It'll make carbon dioxide and water. So these are our least useful reactions because they're not transformative into another organic compound. It's not a controlled reaction. It doesn't matter what organic compound we use. When you burn it, you're going to make carbon dioxide and water and destroy that organic molecule. It's not a directed, controlled reaction like the rest of the ones that we're going to talk about. The first real organic reaction that we want to deal with are the addition reactions. Here we're really caring about structure, what's exactly happening. And the functional group that we want to associate with performing addition reactions are the alkenes. And we're going to do some examples of addition reactions for alkenes. But in every single addition reaction that we're going to look at, the following things will always occur, and we're going to see this in each addition reaction that we look at. The first thing we're going to look at is each carbon of the carbon-carbon double bond will have something new added to it. That's where the name addition reaction comes from. You're adding in to each of the carbons of the carbon-carbon double bond. But you have to remember that carbon only has 4 bonds, so if we're trying to make a new bond, we have to get rid of an old bond. So the second thing we're going to see in every one of these addition reactions is that in order to maintain the 4 bonds of carbon, in order to add something new to the carbons, we have to get rid of something old. And the old thing we're going to get rid of is the carbon-carbon double bond. That carbon-carbon double bond is going to be transformed into a carbon-carbon single bond. That's the bonds we lose in order to make room for the new bond. And then the last thing we're going to see with all of our addition reactions, and quite frankly, we can even be more general, the other reactions we're going to do as well, the rest of the molecule is going to remain unchanged. That's that kind of train engine and boxcar analogy. It's the engine that's doing the work. Wherever the engine goes, the rest of the boxcars are going to go with it on a train. Well, same thing happens for the rest of the molecule. The changes are going to happen at the functional group. The rest of the molecule is going to remain unchanged. So here we have several addition reactions that we want to look at. And where you first want to draw your attention is the left-hand part of the screen and noticing that alkene. So we're looking at the left part of the screen. Notice that we have an alkene pointed to with the red arrow. So we're starting with an alkene. What we want to do for this is I'm going to show you 3 different addition reactions, but we're going to use the same alkene so you can really start to see the general things that are going to happen in every single addition reaction. So we want to look at that alkene on the left-hand side of the screen. Now, what I did is I boxed in the functional group. In that red box, you see the functional group. And that's where we're going to see all of the changes happening. So the first type of reaction that we want to look at is the one going across the top. And the one going across the top is sometimes called a halogenation. So across the top here, we're going to do a halogenation. And that's a specific type of addition reaction. We're going to add in halogens. Remember what halogens are. Halogens are those elements in group 7A. Fluorine, chlorine, bromine, iodine. So to generalize it, we're going to have halogens represented with X's. That means it could be F2, it could be Cl2, it could be Br2, or it could be I2. Any of the halogens will work for this. So across the top, we're adding two halogens represented by the X's. So we want to look and we want to see, okay, what are the changes that are going to be taking place? Well, the first change that we said was going to take place was we were going to add two things to the carbon of the carbon-carbon double bond. So we're adding two things in. Let's see that in this reaction. So the two things we're adding in, so now highlighted in yellow, we're adding in a halogen. What's going to happen? We're going to add in a halogen to each one of the carbons of the carbon-carbon double bond. So we see that happening in that upper right-hand structure. Highlighted in yellow again, we can see we added a halogen to each one of the carbons of that carbon-carbon double bond. So that first thing that always happens in an addition reaction happened here. Remember, the only changes we're looking for are inside that red box. We added those halogens. Well, the second thing we talked about as happening in every single one of these addition reactions is in order to make room for the new bonds that are being formed between the carbon and the halogen, we had to get rid of an old bond. Well, what's the old bond that we got rid of? Well, the old bond that we get rid of is the carbon-carbon double bond becomes a carbon-carbon single bond. We're going to see this. I'm going to highlight this aspect in green. Starting with the alkene, I'm highlighting that carbon-carbon double bond. Now we look at the product, upper right-hand part of the screen. Notice how that carbon-carbon double bond became a carbon-carbon single bond. So that's the second thing that happened. Remember, first thing is we added in the halogens. Second thing that always is going to happen is we're going to reduce the carbon-carbon double bond to a carbon-carbon single bond. And there's a third thing that will always happen for each one of these addition reactions. What's that third thing? Well, the third thing is that the rest of the molecule is going to remain unchanged. So now we're looking at that area outside of the red box, the rest of the molecule. Well, kind of underlined in blue, I underlined the rest of the molecule for that starting alkene. Well, if we look at our product in our upper right-hand part of the screen, what do we notice? Nothing changed with that. We had the same connectivity as we did before. Kind of in a non-chemistry analogy, how we want to think about some of these reactions is almost the way you would think about an ancient or medieval scribe. In ancient or medieval times, a scribe's job was to completely and accurately copy what they were looking at. They were the copy machines of that age, of that day. Completely and accurately copy it without making any changes. That's what's happening to the rest of the molecule, is that nothing is going to be changed in that rest of the molecule. So here we can see those things that happen in going from the alkene when we did this addition reaction. We added the halogens, one to each of the carbons of the carbon-carbon double bond. The carbon-carbon double bond became a carbon-carbon single bond, and we didn't do anything to the rest of the molecule. So that's our first addition reaction running across the top. The next addition reaction we want to look at is the one running across the middle of the screen. And running across the middle, we're adding something a little bit different. So I'm highlighting this in yellow. We're highlighting HX. X is still a halogen. So here we're adding two different things. We're adding a hydrogen and we're adding a halogen. This sometimes gets called a hydrohalogenation, because we're adding both hydrogen and a halogen to it. So you may run across that term of hydrohalogenation. So here we have two different options because we're adding two different things, a hydrogen and a halogen. So it don't matter which one goes in which spot. We would make different products. Now, we're not going to worry about which one is favored, which one is dominating. You actually end up getting more of one than the other. That sort of detail is beyond our scope. I just want you to recognize that there will be two different possibilities here for this. So we're going to do the same thing for this one that we did in the previous one. We're going to look for those three things that happen for every single addition reaction. Every single addition reaction that you will look at, you will see the addition of two things to the carbons of the carbon-carbon double bond, this time a hydrogen and a halogen. So let's look at it. So we get two choices if you look over to the right. So I'm going to highlight in yellow those additions. Well, first choice is we could add the halogen to the interior carbon, highlighting that in yellow, and then we could add the hydrogen to the end carbon. Notice how now we have 3 hydrogens on that carbon when we started with 2. So we definitely added both things. Remember, we could have done this the other way. So there's another option. I could have, so right below it, again I'm highlighting in yellow, we could have added the halogen to the end carbon instead and added the hydrogen to the interior carbon. That was also a possibility. Okay? You see we're going to get slightly different products. They would be isomers of each other depending upon which one we added to which position. But we still have that adding. We still have that addition. We added one thing to each of the carbons of that carbon-carbon double bond. What has to happen to make room for those new bonds? Well, we have to lose an old bond. Which old bond did we lose? Well, the carbon-carbon double bond becomes a carbon-carbon single bond. I'm going to highlight that in green. Our carbon-carbon double bond became a carbon-carbon single bond in our two choices for products. So we still see that happening. Third thing that's going to happen, or maybe more appropriately not happen, is the rest of the molecule is going to be unchanged. So I'm going to show this with an underlining in blue. The rest of this molecule, no changes took place to the rest of the molecule. The only changes are taking place at the functional group, what I've boxed in red on the screen for. So here, because we're adding hydrogen and a halogen, there's two different choices for which one will go where. This just shows each of those choices. I'm going to do one more addition reaction, again starting with the same alkene on the left. This time we're going to be adding hydrogen, H2. So adding hydrogen is sometimes called a, probably can already recognize what this is going to be called, sometimes this is called a hydrogenation. It's just a specific type of addition reaction. So this is sometimes called a hydrogenation. Now this hydrogenation happens very, very slowly. The first two that we talked about across the top and the middle, the halogenation and the hydrohalogenation, happen really quickly. And it doesn't take a long time. The reaction across the bottom is very, very slow. Because that reaction is very, very slow, we have to speed it up for it to be practically useful. So kind of boxed in purple, what I have is what's happening in this reaction. Sometimes you have to add in something else just to speed up the reaction. And often palladium or platinum is used as a catalyst since this reaction is so slow. Now this is our first exposure to what catalysts are, what they do. Catalysts speed up reactions. Okay? they make reactions go faster. And they do that in a couple different ways that we're not going to get into the details right now with. But the key thing about catalysts is they don't change what product you're going to make. They don't appear in the product. One way of thinking about this is the same way you would a human matchmaker. Okay? If you are a matchmaker, your job is to set up people together to form a couple. Well, your job as a matchmaker, you're now not part of that relationship. It's not now some bizarre love triangle. Your job as a matchmaker is to get those two people together. Well, that's the job of the catalyst. The job of the catalyst is just to get these things to react faster than they would be able to react on their own. They don't become part of that product. So again, these things that we're going to see for addition reactions are going to happen here. We're going to add things to the carbon-carbon double bond. In this case, what are we adding? We're going to add two hydrogens. So we're going to add hydrogens to the carbons of the carbon-carbon double bond, highlighted in yellow. You can compare that bottom right-hand structure with that starting alkene. I have two hydrogens on that interior carbon now. When I started with one, I added a hydrogen. I now, in my product, have three hydrogens on that end carbon. I started with two. So I added to my carbon-carbon double bond, which is what's going to happen in every single addition reaction. In order to make room for those new bonds, what had to happen? Well, what had to happen is my carbon-carbon double bond had to become a carbon-carbon single bond. Highlighting that in green, you can see that that change still happened. And the last thing that we want to look for these addition reactions is the rest of the molecule remained unchanged. And I'm going to underline in blue. You can see that the rest of the molecule remained unchanged. So in every single addition reaction that you're looking at, those three things are going to happen, regardless of whether it's a halogenation, a hydrohalogenation, or a hydrogenation. You're always going to add to both of the carbons of the carbon-carbon double bond. The carbon-carbon double bond is going to become a carbon-carbon single bond, and then you're not going to make any changes to the rest of that molecule. Next, we want to look at the oxidation of alcohols, aldehydes, and ketones. So in a similar way to what we did for the addition reactions, we're going to do something similar for the oxidations, in that there's some general things that will happen in every oxidation reaction when we're dealing with alcohols, aldehydes, and ketones. So in these oxidations, the following three things are going to occur. We're going to add a carbon-oxygen bond. So that's what we're going to increase. We're going to increase the number of carbon-oxygen bonds. We're going to see that we're going to make room for that new carbon-oxygen bond, lose a carbon-hydrogen bond. And then in a similar process, besides the functional group, the rest of the molecule is going to remain unchanged. So we're going to look at some examples of what will happen with this. So we're going to see that primary alcohols are going to be oxidized first to aldehydes, then carboxylic acids. Secondary alcohols will oxidize to form ketones. We're going to see that tertiary alcohols will not oxidize, and that's why it's important to recognize what classification of alcohol you're dealing with, because each different type, primary, secondary, and tertiary, are going to react differently. Aldehydes will oxidize the carboxylic acids, and ketones end up not oxidizing. So our first oxidation example involves a primary alcohol. So if we look in the top left-hand corner, we recognize it's an alcohol. This one ends up being a primary alcohol that we are looking at for this, because there's only one other carbon attached to the carbon that has the OH. Now, oxidations are pretty complex. We're not looking at the details or the mechanism for that. So to symbolize that we're going to perform an oxidation without worrying about what the other thing we're adding, what you'll often see, and I'm using the red arrow to point at this, is you'll often just see an O in brackets. And what that O in brackets mean is that you're trying to perform an oxidation, but you're not specifically saying what the other thing you're adding is. And in that way, we can look at some of the general characteristics of oxidations without worrying about the specific mechanistic details, which are really beyond the scope of us. That's more of a 200 level full year organic conversation. That's kind of, we don't need to go to that level of detail. So what we're looking at when we're doing an oxidation is that O in brackets. Okay? Now, the first thing that happens when we oxidize a primary alcohol is that we end up forming an aldehyde. So in the upper right, you're going to see an aldehyde getting formed. So again, similar thing. We're only changing the functional group. That's the only thing that is happening for this. Okay? So inside the red boxes are where the changes are going to occur. Now remember, we said we were going to see three things happen in every oxidation. One, we are going to increase the number of carbon-oxygen bonds. We're going to add one. So I'm going to show this in yellow. If we look back to our starting primary alcohol in the upper left-hand part, in yellow, I'm highlighting that carbon-oxygen bond. You see we have one bond between carbon and oxygen. Now if I look at that aldehyde product in the upper right-hand corner, what do we see? We see a carbon-oxygen double bond here. So we have two bonds between the carbon and the oxygen. We see that we have changed the number of carbon-oxygen bonds from 1 to 2. We increase that number. The second thing that we're going to end up seeing, I'm going to highlight this in green, is in order to make room for that new carbon-oxygen bond, we had to get rid of a carbon-hydrogen bond. So if I look at that primary alcohol, notice that I have two hydrogens bonded to that carbon in that primary alcohol. How many hydrogens do I have bonded to that carbon in the aldehyde product? Just one. So I lost that carbon-hydrogen bond. So I gained a carbon-oxygen bond. I lost a carbon-hydrogen bond. What else are we going to see? Well, we're going to see that the rest of the molecule remains unchanged. So I'm going to underline the rest of the molecule in blue. And we can see that there are no changes that happened in going from reactant to product. Now, the reaction doesn't stop there. The aldehyde is what's really termed an intermediate. It does form, but if you were performing this reaction in an actual lab, if you were physically doing this, you wouldn't see the aldehyde because this aldehyde is going to undergo further reactions. This aldehyde is going to oxidize as well. Now remember, the same things that are going to happen. Every time we have an oxidation, we increase the number of carbon-oxygen bonds, we decrease the number of carbon-hydrogen bonds, and the rest of the molecule is going to remain the same. Again, the changes are going to occur inside the red box, the functional group. So when we take this aldehyde and perform another oxidation with it, we're going to get the structure you see on the bottom. So let's highlight those key things. We should see an increase in the number of carbon-oxygen bonds. Well, I already have two. I'm highlighting yellow. I can't add a third bond between that carbon and that oxygen because oxygen can only have two bonds, but I'm introducing a new oxygen. So I still have three bonds between carbon and oxygens. I increase the number of carbon-oxygen bonds. Where does that other oxygen come from? Where did that new oxygen come from? Well, it came from this specific oxidizing agent that we're not able to get into the details on because that's kind of beyond our scope. So that new oxygen came from that oxidizing agent, that thing we added that we're not looking at the details of. But you can see highlighted in yellow, I went from 2 carbon-oxygen bonds to 3 carbon-oxygen bonds. I increased the number of carbon-oxygen bonds. In order to make room for that, I had to decrease my number of carbon-hydrogen bonds. I had to lose a carbon-hydrogen bond. Looking in the upper right-hand corner, you can see I have 1 hydrogen attached to the carbon in the aldehyde. Look in the product. I don't have any hydrogens bonded to that carbon now, so I definitely lost a carbon-hydrogen bond. Third thing that we're looking to see is that the rest of the molecule remains unchanged. So highlighted in blue again, you can see that the rest of the molecule, no changes actually happened for the rest of the molecule here. They remained unchanged. So when you oxidize a primary alcohol, what you ultimately get at the end is a carboxylic acid. Yes, an aldehyde initially forms, but that then quickly undergoes an oxidation such that your final product is that carboxylic acid. So this shows what happens with a primary alcohol. Now we want to see what happens with a secondary alcohol. So here we're looking at what's going to happen for a secondary alcohol. And if you look in the upper right-hand corner of the screen, you're going to see that we definitely have a secondary alcohol. We recognize that because we're counting the number of carbons that are directly attached to the carbon that has the OH. Remember, if you need to review, you should go back to the previous video where we classified alcohols to kind of review classifying primary, secondary, tertiary. So again, the changes are going to happen at the functional group. That's where all of our changes end up happening at. So when we oxidize a secondary alcohol, what we're going to see is that they're going to form ketones. And we can see that structure in the upper right-hand corner. Oxidize a secondary alcohol, you will end up forming a ketone. So now let's look at the steps that actually kind of happen, the changes that actually occur. Well, we said one thing that happens in every oxidation of these is that we're going to increase the number of carbon-oxygen bonds. So I'm going to highlight these in yellow. In the secondary alcohol, I see I have 1 bond between carbon and oxygen. I look over to the right at the ketone. Now I have 2 bonds. I definitely increase the number of carbon-oxygen bonds. In order to make room for that new carbon-oxygen bond, I had to get rid of a carbon-hydrogen bond. I'm going to show this in the green. Here I have 1 hydrogen attached to that carbon. In the product ketone, notice I don't have any. Last thing that you're going to see is that the rest of the molecule is going to remain unchanged. So kind of underlined in blue here, I have the rest of the molecule. And you can see that going from reactants to products, none of the rest of the molecule changed. The only change happened inside that red box. So when you oxidize a secondary alcohol, you will form a ketone. At the bottom, we look at the last type of alcohol that we have. At the very bottom, you see we have a tertiary alcohol. This alcohol in the bottom left is a tertiary alcohol. And what we're seeing is that tertiary alcohols will not oxidize. So you get no reaction when you try to oxidize a tertiary alcohol. Nothing's going to happen. It'll just remain a tertiary alcohol. These tertiary alcohols cannot be oxidized. And we can kind of understand why. Because what has to happen in an oxidation? Well, in an oxidation, what has to happen is we're increasing the number of carbon-oxygen bonds. Okay? But in order to make room for that more carbon-oxygen bonds, we had to lose a carbon-hydrogen bond. Look at that carbon that I'm pointing at with that red arrow. There are no hydrogens attached to that carbon. Because there are no hydrogens attached to that carbon, I can't lose the carbon-hydrogen bond in order to make room for a new carbon-oxygen bond. And that's why your tertiary alcohols will not oxidize. They don't have that carbon-hydrogen bond that we're able to get rid of and remove. So secondary alcohols will oxidize the ketones. Tertiary alcohols will not oxidize. There's no reaction. They will remain unchanged. You cannot oxidize that tertiary alcohol. So we've kind of already seen what's going to happen for aldehydes and ketones based upon what's happened with primary, secondary, and tertiary alcohols. But let's just do an additional reaction for this. Another example to show this. So in the upper left-hand part of the screen, the molecule that I have is an aldehyde. And if you followed what happened with primary alcohols, well, you saw that primary alcohols quickly oxidize to form an aldehyde, but then that aldehyde then also oxidized to form a carboxylic acid. Well, if you started with an aldehyde and tried to oxidize it, that aldehyde is just going to oxidize to form that carboxylic acid that we see in the upper right-hand corner. You know, kind of almost skipping a step because we're already starting with an aldehyde. We know that aldehydes will oxidize to carboxylic acids. Can we see those same steps? Well, we can see the same steps that we talked about because it's the same thing that happened when we went through that full primary alcohol oxidation. What do? We increased the number of carbon-oxygen bonds. We started with 2, highlighted in yellow. Now we went up to 3. Remember where that extra oxygen came from? It came from the oxidizing agent. We're not worried about the specific details for that. To make room for that new carbon-oxygen bond, what did we have to do? We had to get rid of a carbon-hydrogen bond. Our aldehyde had 1 carbon-hydrogen bond. Our carboxylic acid, when you look at it, doesn't have any. Third thing that happened is the rest of the molecule. The rest of the molecule will remain unchanged. I'm going to underline that in blue. You're going to see that everything outside of the box did not change. It's only the functional groups that end up changing. So that's what happens to aldehydes. For ketones, we're seeing what happens with a ketone across the bottom. Ketones do not oxidize. And that kind of makes sense if you think back to what happened to a secondary alcohol. Secondary alcohol oxidized to form a ketone, but then it stopped there. We didn't show any more oxidations that would happen. And that's because ketones do not oxidize. And we can kind of look at why ketones don't oxidize. Well, in order to oxidize, you need to lose a carbon-hydrogen bond. Look at this carbon underlined in green. That's the carbon of the ketone. We don't have any hydrogens bonded to it. So that means we can't perform that oxidation. So ketones will not oxidize. There's one more type of oxidation, and this one works a little bit differently than the oxidations we just talked about. This is the oxidation of thiols. Thiols end up oxidizing a little bit differently than some of the other functional groups that we just talked about, so we're going to treat them separately. What happens with a thiol is thiols oxidatively couple. And what that means is that 2 thiols will combine and form a new thing, a disulfide. You can think about this as linking 2 thiols together. In a thiol oxidation, the following things are going to happen. you're going to form a new sulfur-sulfur bond between the two thiol molecules. In order to form that new bond, you have to get rid of an old bond still. So that means the sulfur hydrogen bond from each thiol will be removed. Remember, we can't make a new bond without breaking an old bond. Sulfur is just like oxygen and will generally have two total bonds in the organic molecules. So let's look at a specific example of how thiols are going to oxidize. So here we look at two thiols that we're going to oxidize. And again, the changes are going to happen at the functional group, boxed in red. So across the top, you see the two thiols. And then going down, I'm going to oxidize them together. So what are we looking for? Well, what are we looking for is we're looking to form a new sulfur-sulfur bond. We're making a new bond between these two thiols. Where's that new bond? I'll highlight it in yellow. We can see that new bond getting formed. We're going to make a bond between these two sulfurs. Those are going to be the points of attachment when we're combining these two molecules together. In order to make room for that new bond that's being formed between those two, they each have to lose an old bond. What old bond will they lose? Well, the sulfur hydrogen bond that I'm highlighting in green. As I go down to the product, notice I don't have any hydrogens bonded there. That's the bond I ended up losing. Last thing that happens is the rest of the molecule will remain unchanged. So I'm kind of underlining that in blue. Unchanged, unchanged. Now here's where you have to start being a little bit careful. It may look like I'm changing the rest of the molecule here, but I'm really not, because here's where you got to use that train engine and locomotive analogy. Think about what sulfur I have. This sulfur that I'm pointing at is really this sulfur. What's really attached to it? Well, what's really attached to it, I'll show with the blue arrow, is a CH2. I need to have a CH2 then attached. So what you're finding is sometimes you're going to have to rotate a molecule either on paper or in your head in order to make sure that things keep the same connections. Okay? I had to rotate one of these sulfurs around in order to get the sulfurs to match up. So you have to be very careful when you're doing that, such that you maintain the same bond connectivities. And sometimes using arrows, using numbers, using letters, using symbols can kind of help make sure you're mapping things up the proper way. So I use red arrows to indicate the sulfurs that were the same. Now what do I have to that sulfur? Well, I have a CH2. Now if I go over, maybe I can just put numbers. 1, 2, 3, 4. Do I have the same connections? 1, 2, 3, 4. Everything is still connected in the proper sequence. I just had to rotate the molecule around. So thiols end up oxidizing to form what we call a disulfide. The next type of reaction that we want to look at are the neutralization reactions. And this is going to work the same way as the neutralization reactions we did in the acid-base chapter in the previous unit. It's just that this time we're dealing with organic molecules. So if we're dealing with acids and bases, just a real quick review of our functional groups. Amines are weak bases, and carboxylic acids are weak acids. They're going to act just like any other weak acid or weak base is going to react. They're just organic versions of weak acids and weak bases. So what we're going to see is that amines will react with strong acids to produce what are called amine salts. and carboxylic acids will react with strong bases to produce carboxylic acid salts. Now, for these neutralization reactions, we have to be very, very careful with them, because these neutralization reactions also happen in the course of other reactions, sometimes when you may not necessarily even be expecting them. So we need to be on the lookout for those. So we're going to see these crop up not just in the specific neutralization reactions we talk about, but anytime we're dealing with a carboxylic acid or an amine, these neutralization reactions can occur. So we have to be cognizant of that and very careful when we're dealing with amines and carboxylic acids, that we're paying attention to what they're paired with, what else they are with. So here we want to look at a neutralization reaction. So the first one across the top deals with an amine. So on the upper left, what you're seeing is an amine. And what are we pairing that with? HBr. Well, HBr is a strong acid. So here we're reacting our amine with our strong acid. And this is just doing what any other acid and base would do in this situation. The amine is the weak base. What is the weak base going to do? The weak base is going to grab H+. Where do we have H+ being available from? Well, it's available from that strong acid. So in yellow, I'm going to be highlighting that amine picking up an H+, and it does it at the nitrogen. If you look kind of in the red box where the changes are happening, I currently have 2 hydrogens attached to the nitrogen. If it picks up an H+, what will I have at the product? I'll have 3 hydrogens and a plus charge. Why? Because I'm grabbing H+. I'm grabbing that positive charge as well. So what you see in the top right-hand corner is what we would call the amine salt. And there's a couple of things to notice here. What we really want to notice is that there's no covalent bond between the nitrogen and the bromine. Look up in that top right-hand structure. There's no line between that nitrogen and the bromine. Remember what these lines are represented. These lines are representing covalent bonds, sharing of the electrons. That's not what's happening here. There's no sharing of the electrons between the nitrogen and the bromine. Instead, we have 2 ionics. It's an ionic attraction. The other thing that we want to notice is that nitrogen now has 4 bonds. Nitrogen is bonded to 3 hydrogens and the carbon to the left. It has 4 bonds. How many bonds does nitrogen usually get? Usually nitrogen only gets 3 bonds. This time it has 4. But because it has an unusual number of bonds, it has 4 bonds instead of the usual 3, it's going to contain a positive charge as a result of having not the normal number of bonds. Remember what salt means. Salt is slang for ionic compounds. So you see the positive and the negative charge for this amine salt. We look at the bottom reaction. For the bottom reaction, what we have is a carboxylic acid. You see across the bottom we have a carboxylic acid. What are we reacting it with? Well, potassium hydroxide, that's a strong base. Well, this is going to undergo that acid-base neutralization reaction. What's going to happen? The acid is going to give up the H+. The base is going to grab the H+. Just like any other acid or base. There's nothing special happening here. It's just these are organic acids or organic bases. So let's look at what happens. Well, here are organic molecules. The acid, that's the carboxylic acid. I'm highlighting the H+ that would be given off. And notice in the product, no H+. So we lost that H+. Where does that H+ go? It was grabbed by the hydroxide ion. So across the right, what you see is the change. What we end up forming is a carboxylic acid salt, an ionic compound. Notice there's no covalent bond between the oxygen and the potassium because they aren't sharing electrons. They're not capable of sharing the electrons. So we get ions, negatively charged oxygen, positively charged potassium. Another thing you want to notice is that oxygen only has one bond. Only thing that oxygen is bonded to is the carbon. Usually we recognize oxygen having two bonds. Because oxygen has an unusual number of bonds, it's going to have a charge. This time it's going to have that negative charge. Not listed here, we didn't specifically write this out, we could have, but water is also formed in this. Where did the water come from? Well, that came from the H plus from the acid with the OH minus from the base. A couple other things we want to notice about these reactions is that, again, the only changes are happening at the functional group, inside the red boxes. We look at the rest of the molecule. On the amine reaction on the top, the rest of the molecule didn't change. Look underneath the purple. No changes happen there. The only changes happen with the functional group. We look at the bottom, underlined in purple again. The rest of the molecule did not undergo any changes for this. So again, we're seeing that theme happen in all of our reactions. The rest of the molecule is going to be unchanged. Now look out for these neutralization reactions to come in as a secondary reaction in some of the other reactions that we're going to be talking about. The next reactions that we want to look at are those involving esters. We're going to do two things with esters. We're going to talk about how to form an ester and then kind of go the opposite way, talk about how to break down an ester, which is sometimes known as hydrolysis. In terms of the formation of an ester, we already have an idea of how esters are formed. We had to learn a little bit about this in order to correctly name them when we did the ester nomenclature. If you think back to the ester nomenclature, we were already hinting that esters are produced from the reaction of a carboxylic acid and an alcohol. So the reverse process, breaking down an ester, is a very slow reaction. So being it's such a slow reaction, we have to speed that reaction up. And we can do that with either acids or bases. But what's going to happen is the products are going to be slightly different based upon whether an acid or base is used. Think back to those neutralization reactions that we just talked about. If an ester is broken down with an acid, the products will be an alcohol and a carboxylic acid. If an ester is broken down with a base, the products are going to be an alcohol, and then the key difference is instead of a carboxylic acid, that neutralization reaction is going to kick in, and we're going to get the salt form of that carboxylic acid. So that's what we mean when we say you have to be careful of these neutralization reactions because they kind of sneak in and make themselves appear in other reactions as well. So we're going to do some specific examples for ester reactions. So here we're going to form an ester. And an ester is always going to get formed from a carboxylic acid and an alcohol. So in the upper left-hand corner of the screen, you see that I wrote out a carboxylic acid. And in the upper right-hand corner, we have an alcohol. So when you combine a carboxylic acid with an alcohol, you will make an ester. And again, the red boxes are boxing in the functional group parts of the molecules. This is where the changes are really going to take place. So we want to kind of go through and show where these parts, where these pieces are coming from. Now remember, every time we look at an ester, we talked about trying to dissect an ester as always dissecting between that C double bond O and the C single bond O. That's what, kind of splits it into the two parts. And remember from the nomenclature, we said the side with the C double bond O was kind of from the carboxylic acid. That's where those pieces of the molecule came from. Meanwhile, the part with the oxygen originally came from the alcohol. So in order to help see where everything fits together, you can kind of do a little bit of color coding to kind of match on what's going to happen. So in this carboxylic acid, I have a red arrow pointing at the C double bond O. Well, the C double bond O of the carboxylic acid is going to be the C double bond O of the ester. What do I have attached to the C double bond O of the carboxylic acid? Well, I can do this with a symbol, I can do this with a number, but to the left, I have a CH3. That means I'm going to have a CH3 in my ester attached to that same position. Now for dealing with the alcohol. And again, there's multiple different ways of doing this with color, symbols, number. I'll kind of show a little bit of each. What I'm doing is I'm just coloring in the oxygen of the alcohol. That oxygen of the alcohol, what does that become? That's going to become the oxygen of the ester. That's how those map onto each other going from reactants to products. Well, what do I have attached to that oxygen of the alcohol? Well, I have a CH2, so I'm just going to do this kind of with numbers in blue. I have a CH2. That means what has to still be attached to that oxygen of the ester? Well, that's CH2. And I can just kind of go through and keep all of my connections the same in order to kind of quickly identify where all of these pieces came from. Because remember, if you're not part of the functional group, you have to maintain the same bond connectivity, the same connections. You can't be changing the bonds in there. Again, notice how I kind of had to flip that alcohol around in order to line it up with what's happening with that ester. So besides making the ester, another thing that gets made is water. Where did this water come from? Well, the water kind of came from the spare parts that we didn't use. What didn't we use from the alcohol? Well, we didn't use a hydrogen from the alcohol. What didn't we use from the carboxylic acid? We didn't use the OH. So that OH and that H combined to form the water. The key thing is when you're doing reactions for yourself is you really need to identify the different parts of the ester and where they came from. Being able to match what you're seeing in reactants to what they're going to form in products. Or looking at a product and trying to figure out where that thing came from in your different pieces, your different reactants. And this is where colors can help, numbers can help, symbols can help, anything that lets you tie in where these different pieces end up going. But a carboxylic acid and an alcohol will always combine to form that ester. Next thing we want to do is kind of the exact opposite of what we did. What we just did is we formed an ester. Now we want to talk about breaking down an ester. So on the left, what you see is I've written out an ester. And we're going to break this down two different ways. Across the top, we'll do it with a strong acid. And across the bottom, we're going to do this with a strong base. So again, when we break down an ester, we're expecting to get a carboxylic acid piece and an alcohol piece, because after all, this is just the reverse process of forming an ester. If it takes an alcohol and a carboxylic acid to form an ester, when we break down an ester, you would expect to get a carboxylic acid and an alcohol out. So let's try to map on and match on what's happening to the different parts of the molecule going from reactants to products. Remember what you want to look for in an ester. Every time you look at an ester, you want to kind of mentally, or maybe even actually dissect the molecule right there in that purple dashed line between the C double bond O and the C single bond O. Because remember, that's going to split the molecule into its different sides, its different pieces. The part with the C double bond O, we recognize that that would originally come from a carboxylic acid. So we're expecting that piece when we break it apart to form a carboxylic acid. And the part with the oxygen kind of came from an alcohol. We're expecting that piece to form an alcohol. So we're expecting carboxylic acid and an alcohol to form. And let's kind of map on what's going to happen. Well, the C double bond O from the ester is going to form the C double bond O of the carboxylic acid. So we could get that in place. What do we have attached to that C double bond O? I'm just going to use red numbers to illustrate that. Well, we would have a CH2 and then a CH3. What are we going to have? That same thing in that same connectivity. CH2, CH3. I didn't change any of my bond connectivity here. So for the alcohol, what's it going to look like? Well, if I just kind of shade in blue the oxygen from the ester, we know that the oxygen from the ester originally comes from the oxygen of the alcohol. That's that mapping onto right there. Well, now I can use blue numbers to kind of see my attachments. What is this oxygen attached to in the ester? Well, it's attached to a CH2. Label that 1. That means I better have that same connectivity in my alcohol. What's that CH2 attached to? It's attached to a CH3. I better have that same connectivity here. So you can see, you can kind of use this to start mapping on what you're going to make. So when you split up an ester using strong acids, you're going to get a carboxylic acid and an alcohol. Now, when you do this in base, you're going to get a slightly different product. The alcohol is still going to be the same. We can still see the alcohol. We can still use our color coding to kind of illustrate that. The oxygen of the ester is going to become the oxygen of the alcohol, and our same kind of bond connectivities are maintained. For the carboxylic acid, the C double bond O is going to become the C double bond O, CH2, CH3, that gets maintained. But what's going to be the difference between acid and base? Well, here's where those neutralization reactions come back into the forefront again. If I form a carboxylic acid, but I'm in the presence of a strong base, well, then that neutralization reaction is actually going to occur. And instead of having the carboxylic acid, I'm going to have that carboxylic acid undergo that neutralization reaction and form the carboxylic acid salt. So remember, when you have carboxylic acids, being they have acidic properties, you have to pay special attention to what else they're with. A carboxylic acid with a base is no longer going to be a carboxylic acid. It's going to undergo that neutralization reaction and produce not the carboxylic acid form, but instead the carboxylic acid salt form, which you see on the bottom. That's the key difference, is when you do this between acid and base, is what form will that carboxylic acid be in? And that depends upon what it's with. You have to keep those neutralization reactions, kind of watch out for them. They're going to show up other places. So the last set of reactions we're going to look at are the amide reactions. And we're going to do something similar to the amides that we just saw for the esters. We saw how to form an ester and then how to break down esters. We're going to do the same thing with the amides. We're going to talk about how amides are formed and how amides will break down. That's hydrolysis again. So amides get produced from the reaction of a carboxylic acid and an amine. That means when we break down an amide, we're expected to form a carboxylic acid and an amine. The breakdown is a very, very slow reaction. So being it's a slow reaction, again, we can speed this up with either acids or bases. But remember, the products are going to be slightly different depending upon whether an acid or a base is used. Think back to that previous neutralization reactions. It's still going to come into play. And what we're going to see when we get to an example of this reaction is that if your amide is broken down with an acid, the products are going to be an amine salt and a carboxylic acid. If your amide is broken down with a base, then your product is going to be an amine and a carboxylic acid salt. Those acid-base reactions that happen with carboxylic acids and amines are going to show up again here, this time as secondary reactions for what happens with our amides. So the first one we want to look at is the formation of an amide. And we said that an amide gets formed from the reaction of a carboxylic acid. So you can see a carboxylic acid in the upper left. In the upper right, you end up seeing an amine. Then on the bottom, when you combine that and react together, that carboxylic acid and that amine, you end up forming that amide that you see on the bottom. So again, the changes are happening with the red boxes. The functional groups are what are really combining. You need to maintain the same bond connectivity in order to achieve that product. So let's kind of look at some mapping. So if we're trying to map on reactants to products and what's actually going to get formed, well, we're going to do something similar with amides that we did with our esters. The key bond in an amide is that bond between the C double bond O and the nitrogen. It's right here where this dashed line is. That's going to split the molecule into its two sides. The side with the C double bond O of the amide, that had to originate from a carboxylic acid. The side with the nitrogen originated from the amine originally. So now you can kind of do some mapping to figure out where pieces are coming from, where pieces are going. I'm going to use a combination of colors, numbers, and symbols to represent that. So this red arrow that I'm drawing at the C double bond O, that C double bond O of the amide, where did it come from? Well, it had to come from the C double bond O of that carboxylic acid. And now I want to look at, what do I have connected? Are my connections the same? And you're able to map on and see that. Well, attached to that C double bond O outside the functional group, what do I have? Well, I'm just going to label it with a red one. I have a CH2. Guess what? I have a CH2. What's connected to that CH2? I have a CH. Let's label that with a red 2. I have a CH. What do I have connected to that CH? Well, I have a CH3 and another CH3. Nothing changed with my connections on that. Now if I look over to the other side, I'll do the amine side kind of in blue. The nitrogen from the amide, the one that's getting pointed to right here, where did that originally come from? Well, that came from the nitrogen of the amine. That's the exact same nitrogen. What's attached to that nitrogen in the amine? CH2. Well, I better have a CH2 connected to that nitrogen in the amide. What do I have connected to that CH2? Use a blue number to represent that, CH3. That means in my product connected to that CH2, I'd better have a CH3. So when you're doing these problems on your own, when it's not already pre-filled out for you, you're going to have to figure out, okay, what is my product going to look like, or what are my reactants going to look like? You kind of want to use colors or symbols or numbers to kind of make sure that you're maintaining the correct bond connectivities to everything. Remember, sometimes you have to rotate molecules around and making sure that you have the same bonds connected. Your bond connectivities outside of the functional group do not change. You may be looking at, where did this water come from? So if I kind of look at the water is also produced in this. Where did this water come from? Well, one of the things that you didn't use from the amine is, notice that you didn't use one of the hydrogens. What didn't you use from the carboxylic acid? You didn't use the OH, so the OH and the H helped form that water. So the last reaction we want to look at is the exact opposite of what we just did. What we just did is we formed an amide from a carboxylic acid and amine. We want to show what happens when we break down an amide. So when we break down an amide, we're expecting to get a carboxylic acid and an amine back. But here's where we have to be careful. We're using strong acids and strong bases. Both carboxylic acids and amines have acid-base properties to them. So we have to be very careful with what form will that carboxylic acid and the amine be in. Will they be in their normal, regular form? Or, because of that acid-base reaction, are they going to exist in that salt form? So that's something to be on the lookout as we go through this. So breaking down an amide is a very slow process. Just putting an amide and water together, those would take forever to break down and react, but they can be sped up with strong acids and strong bases. So we're going to show that. Strong acids across the top, strong bases across the bottom. So anytime we are looking at an amide, remember, we want to dissect the molecule between that C double bond O and the nitrogen. That's going to split the two sides of the molecule. The side with the C double bond O, well, that's the side that's going to form the carboxylic acid. The side with the nitrogen, that's going to form the amine in that product. So as we're kind of looking at what's going to form, well, we can start mapping things on. So we expect a carboxylic acid and an amine. So across the top, that C double bond O of the amide, what's that going to form? The one pointed at with the red arrow? Well, that's going to form the C double bond O of that carboxylic acid. What do I have attached to that C double bond O of the amide? Well, I'm just going to label it with a red 1. I have a CH3. I better have a CH3 attached in my product. So now we're looking at the amine side. The nitrogen, using the blue arrow now, from the amine is going to, or the blue arrow pointed at the nitrogen from the amide is going to form the amine in the product. What do we have attached to that nitrogen? Well, I have a CH2. I have another CH2. And then a CH3, I need to maintain that bond connectivity. But I'm not going to form the amine here. Instead of forming the amine, I'm going to form the amine salt. Why am I going to form the salt version? Well, because I'm in strong acid. Amine plus strong acid is going to give you not the free amine, but instead I'm going to form the amine salt to go along with my carboxylic acid. So when you break down an amide using water and a strong acid, you will get a carboxylic acid and the amine salt. Now across the bottom, we're going to look at what happens when we do this with strong base. Well, we're expecting a carboxylic acid and an amine, and the bond connectivities are the same. The C double bond O of the amide is going to become the C double bond O of the carboxylic acid. What do I have attached to it? CH3. But here, I'm forming a carboxylic acid, but I'm in strong base. Well, carboxylic acid plus strong base isn't going to stay as a carboxylic acid. Instead, we're going to be looking at the salt form. So instead of forming the carboxylic acid, I'm going to form that carboxylic acid salt is going to get formed instead. Now, kind of mapping things on for what's happening with the amine, the nitrogen from the amide is going to form the nitrogen from the amine. What do I have connected to that nitrogen? Well, I have a CH2. I better have a CH2 in my product. What's connected to that CH2? Another CH2. I better have that CH2 in my product. What is connected to that CH2? CH3. I better have that connected in my product. So you can use colors, numbers, symbols to help you orient yourself and make sure that you're maintaining the same bond connectivity. So when you're breaking down an amide, you're going to form a carboxylic acid and an amine. You just have to ask yourself then, anytime I have a carboxylic acid and amine, what form will it be in? Okay, I have to keep those neutralization reactions kind of in mind and be thinking about that. Is it going to be in its regular form, or is it going to be in that salt form? Because again, I'm highlighting this in green. Notice you get slightly different products based upon whether it's done in acid or a base. And the reason behind that is that acid-base properties of amine and carboxylic acid show up again. Those neutralization reactions aren't just present whenever you're doing a neutralization. They can be present anytime you have a carboxylic acid or an amine. You have to really pay attention to what else do you have, because that's going to determine whether it's in its regular form or whether it's in its salt form.